After this introduction, let's now look into the application of high temperature storage starting with solar thermal power plants. The following graphic shows a simplified flow diagram of such a power plant. As you learned already in the lectures on solar thermal power plants, these plants work much like conventional power plants with turbine cycles, preferably with steam turbines. In solar thermal power plants, the heat for operating the steam cycle is not generated by burning any fuel, but by means of concentrated solar radiation. Temperatures of several hundred degrees are thus generated in the solar field, and the heat collected is converted into electricity in the steam turbine with an attached generator. However, the heat collected in this way can also be temporarily stored in a high-temperature heat storage facility before being converted into electricity. This concept is already being used very successfully in the Sunbelt in countries with high solar radiation. The importance of this concept for the global storage market is shown in the following chart. Here you see the worldwide installed capacity of storage in the electricity market as of 2018. The market is currently clearly dominated by pumped storage power plants. However, what we can also see here is that thermal storage is equally as important as battery storage, which means that this is already a widespread technology, also it is not as well known as batteries. In the following, we will take a look at the individual technologies that are being used on the market or about to be used commercially. We will distinguish here again between direct and indirect storage systems. And I want to start with the direct storage concepts. A direct storage is always a sensible storage where a medium is heated and then the medium is stored directly in a tank or vessel for later use. The world's first commercially operated large-scale storage in solar thermal power plants was built back in 1984 at the C04 plant in Daggett, California. The plant had an electrical output of 15 MW. A mineral oil was used here as the heat transfer and storage medium. The oil can be operated up to approximately 320 degrees C without pressurizing. A two-tank storage system was used here, where hot and cold oil are stored separately in individual tanks. This plant has now been shut down after about 30 years of successful operation. This concept is very simple and also very cost-effective due to its direct storage and the favorable properties of the mineral oil. However, its application is limited to only 320 degrees C, which means that only relatively low power plant efficiencies can be achieved. Therefore, the C04 power plant had also integrated a fossil reheater to increase the temperature for turbine operation. However, for this reason, this concept has not been pursued further. Higher temperatures and therefore better efficiencies can be achieved with liquid salt. In solar tower power plants, liquid salt is applied in direct storage concepts. A salt mixture of sodium and potassium nitrate is used here. This specific mixture is now referred to on the market as solar salt. In this concept, the salt is pumped through the solar receiver, where it is heated up to 565 degrees C and then fed into the hot storage tank. If electricity is to be produced, the salt is removed from the hot tank and the heat is extracted in a steam generator. During this process, the salt cools down to 290 degrees C and is then stored in the cold storage tank until sufficient radiation is available again for heating. Radiation supply and electricity production can thus be decoupled from each other. The separation of cold and hot salt into two tanks has the advantage that there is no mixing of the cold and hot salt like in a one-tank system, which might compromise the exergetic efficiency. Since each of the two tanks can hold the entire salt volume, there is also the advantage that in the event of repair or maintenance work on one of the tanks, the complete volume of the salt can be temporarily stored in the other tank. Since salt has a relatively high crystallization point of about 221 degrees C, the tanks must be trace heated to prevent freezing during longer downtimes. This is usually done by heating elements that are inserted into the tank. This concept was first developed and tested in the 1990s at the C02 plant in California. And it was used commercially for the first time in the Gema solar plant in Spain. The electrical output of this plant is 19 megawatts. The salt storage is sized so that the turbine can operate at full load for another 15 hours without solar input. This enables 24-hour operation at least on sunny days. The plant was commissioned in 2011 and has been feeding electricity into the public grid ever since. In the meantime, plants in the 100 megawatt class are also being built using this concept. For example, the C04 power plant in Morocco, which has an electrical output of 150 megawatt and a storage with a capacity of 7 full load hours. We can see from these examples that this is quite a successful concept. Good power plant efficiencies can be achieved with the temperatures obtained. Only the high crystallization temperature requires additional safety precautions. On the one hand, electrical trace heating is necessary. On the other hand, the receiver is drained during downtime so that the salt does not cool down too much and freezes during these periods. Another concept for direct storage is the steam storage. In this concept, water is being evaporated in a solar receiver and the steam is then stored in a steam accumulator. The steam accumulator works according to the so-called Ruth principle. Storage takes place here only at saturation temperature. A certain amount of water is always remaining in the tank at saturation temperature. The steam generated in the solar receiver condenses when it is fed into the tank, raising the water level in the reservoir. The pressure and temperature in the storage will then increase. Pressure and temperature always correspond to the respective saturation steam condition. For withdrawal from the storage, saturated steam is removed from the tank. During this, the pressure in the storage tank decreases, which in turn causes a certain amount of water to evaporate. The heat for evaporation is taken from the stored water. The volume of the water in the storage tank is thereby reduced. Thus, only saturated steam can be withdrawn from such a storage. However, steam turbines usually operate with superheated steam, as the efficiency is then significantly higher. The efficiency of saturated steam turbines is relatively low. So far, this principle has only been used in the two solar power plants PS10 and PS20. In the foreground, we can see the steam tanks before installation. To summarize, in a steam storage tank, steam can be stored directly and even superheated steam can be fed into the tank. However, only saturated steam can be extracted in this concept, leading to poor turbine efficiencies. In addition, the storage tanks must be pressurized so that only relatively small tank volumes can be realized. Therefore, this concept has not gained wide acceptance on the energy storage market.